In this tutorial on the properties of triangles, we are going to basically study the behavior of angles, that how do angles change when we change the line segments that are directly opposite to those angles. And the best way to understand that behavior is by understanding this theorem that is in front of us. This theorem states that the angles opposite to the equal sides of an isosceles triangle are equal. What does it mean? Let's say we have a triangle ABC, okay? And in this triangle, the line segment AB is equal to the line segment AC. So these two sides are equal. And we have this measurement written right here. The line segment AB measures 9.48 centimeter, and so does the line segment AC. By the way, keep in mind that this is a scaled drawing, okay? So what we want to prove is the angle B in this triangle, the isosceles triangle that we have, is equal to the angle C, because these two sides that are directly opposite to these angles are equal, right? So our objective is to prove that the measure of angle ABC is equal to the measure of angle AC and B, okay? And what is given to us is the line segment AB is equal to line segment AC. This is given, and let's say this is my condition 1. So let's do this. Let's drop a line, a perpendicular bisector from vertex A onto the line segment BC. So let's say that this perpendicular bisector intersects the line segment BC at point D. And just because it is a perpendicular bisector, that means the measure of the base angle where these two lines, the line segment AD and BC, are intersecting will be 90 degrees. And since it is a bisector, that means the angle A made at vertex will be divided equally in two parts, okay? So let's say the measure of that angle is X degree. We do not need the precise measurement. We just need to know that these two angles are equal. So this means that the angle BA and D will be equal to angle DA and C. And by the way of this bisector, what we have done is we have created two triangles. One of them is AB and D, and the second triangle is A, D, and C. Okay, we are going to prove that these two triangles are congruent to each other. So what we know is, so far, AB is equal to AC, right? This is given to us right from here. So this is given and it's condition 1. And we also know that the measure of angle BAD is equal to the measure of angle DAC. And this is, I will say, my condition 2. By the way, let me write here as well. This is our condition number 2 by the way of this bisector, correct? And also know that the line segment AD is common here. So that means we can easily say that AD is equal to AD, and this is by the way of our given line bisector that we had. So basically, with the help of these three conditions, you can say very easily that we have two triangles in which one corresponding side is equal, one corresponding angle is equal, and then we have another corresponding side equal. That means using the help of this SAS criteria, we can say that these two triangles, the triangle A, B, and D, is congruent to triangle ADC, right? So in congruent triangles, we can say very easily that all the corresponding angles will also be equal. That means the measure of angle ABC is equal to the measure of angle A, C, and B. And this is what we wanted to prove, right? This is from here. So now that we have proven this theorem, what it really means to us is that if we change the relative measure of these line segments AB and AC with respect to each other, then the corresponding measure of the angles opposite to those sides will also change in proportion to what we are changing the line segment. So I'm going to make use of a dynamic tool in which the measure of angle changes as we change the line segments, okay? So take a look at this diagram in which we have a triangle ABC, okay? So as you see, the line segment AB and AC, they are equal to 8.54 centimeter, right? And because these two line segments are equal, the measure of the angles, which is directly opposite to these sides, is also equal, right? They both are 54.08 degree, right? So let us do this. Let's change the line segment AB and make it longer than the line segment AC. Okay, so I'm moving the vertex A. So as you see that as I'm moving the vertices, these measures are changing. Okay, so let's move it up to this point. Okay, now line segment AB is 10.52 centimeter, is longer than the line segment AC. And you see what happens to the angles that are directly opposite to those sides. So the measure of angle C, which is directly opposite to the longer side, is bigger than the other angle, right? So let's keep increasing and see what happens. If you increase it further, you will notice that the angle keeps increasing. So as you make one line segment bigger than the other line segment, the angle opposite to the longer side will be bigger than the angle opposite to the smaller side. And that's all we wanted to prove in this theorem. If I move it back to my very first original position, now we are back to our isosceles triangle in which we had AB equal to AC and their angles B and angles C are also equal. Okay, so with the help of this, we can make a very good and easy conclusion that if the two sides of triangle are unequal, then the angle opposite to the longer side is going to be larger than the angle opposite to the smaller side. And we observed that with the help of a dynamic tool that we had in which the angles were changing as we were changing the line segments. Okay. So now let us take a look at one example in which we will use this theorem and we will try to prove the congruency of one triangle versus another triangle. Okay. So let's take a look at that example. So in this problem, we are given that there is a triangle PQR and L, N and M are the midpoints of those respective sides. Now we need to prove two different things here. We need to prove that triangle PLN is congruent to the triangle MRN, and the second is prove that the line segment LN is equal to the line segment MN. Okay. So let us first state what is given to us, that there is a line segment. If PQ is equal to QR, we have to prove this, which is what we wanted to prove here, right? And we wanted to prove this. Now we know that the segment PQ is equal to QR, right? In addition to that, we have been told that the M and L are also the midpoints of their respective sides. That means I can divide PQ into two parts. That is PL plus LQ is equal to QM plus MR. L is the midpoint of this segment PQ. That means I can rewrite this sentence as twice of PL, because PL will be equal to LQ, right? So twice of PL is equal to twice of MR, because the line segment MR is going to be equal to the line segment QM, right? Or in other words, you can simply cancel out 2 from both sides of this equation and we can conclude that PL is equal to MR. And this is what you can label as your finding number 1. Okay. Now let us take a look at the second finding. It is that we have this dimension PQ is equal to QR in the triangle PQ and R, right? And there is a property in triangle in which we state that if there are two sides that are equal, then the angles opposite to those sides will also be equal. That means the angle opposite to the side PQ will be angle at R, and angle opposite to the side QR will be angle P, and those will be equal because of the equal sides, right? PQ is equal to QR. This is given. So that can be taken as my finding number 2, all right? And finally, you can also state that there is a midpoint N, which is midpoint of the segment PR. That means the segment PN is going to be NR. So this can be regarded as your finding number 3. Okay. So now let us summarize our findings. I have a triangle PLN, and then I also have a triangle MR and N. What do we collect so far based on these 3 findings? First, we can tell that the side PL is equal to the side MR. From our finding number 1, let's label it. PL is equal to MR. Okay. Angle P is equal to angle R. This is our finding number 2, right? These are also equal. So let's put a label here as well. These two angles are equal to each other. So let me put that in deep blue there. All right. So then we have the third thing, which is the side PN is equal to NR. This was our finding number 3. And this is my PN and this is my NR. Now you have two triangles PLN and then there is a triangle MRN. You have a side, you have an angle, and you have a side equal to each other. So based on the SAS criteria, we can say very easily that these two triangles will be congruent to each other. So this proves our objective number 1. Now since these two triangles are congruent, that means their respective sides will also be equal to each other, right? That means the side LN will be equal to the side what is known as MN, because that is the only remaining side so far. And this will let us prove that the side LN is equal in dimension to the side MN. And this was our second objective that we wanted to prove here. So you see that by the way of this criteria of SAS, we were able to prove whatever we wanted in this case, even though you were not given any dimensions whatsoever of any of these triangles, but you were given some conditions here, and using those, we were able to prove these two objectives that we wanted to prove.